Good morning and welcome to my research proposal oral presentation on a mixed methods study to compare the impact of virtual and concrete manipulatives in mathematics instruction. Introduction to the research problem. I have two reasons for picking this topic for my study. The first is that in my role as an instructional coach in Ontario, I've had many conversations with teachers about concrete and virtual manipulatives, and many teachers prefer concrete manipulatives, and the most common reason given is the tactile nature of the manipulative. And while I agree that the tactile aspect of these manipulatives is wonderful and necessary, I think that maybe many teachers don't know enough about the virtual manipulatives, or are maybe a little frightened of them, and so they're going with what they know, because I see real value to the virtual type. Also, I had an experience earlier this year teaching algebra, specifically solving equations, in one of my grade 7 classes here in Columbia. And one of my students, arguably the student I have who struggles the most with mathematics on a regular basis, had a real aha moment when she used a virtual manipulative, which I will be showing later on in this presentation. As we get going, my theoretical framework will consist of the following ideas: conceptual understanding versus procedural knowledge in mathematics, concrete representational abstract continuum in the place of manipulatives in it, virtual manipulatives, what they are and what they are not, and how virtual manipulatives fit into the CRA continuum. My focus will be on measuring the impact of virtual manipulatives, in this case algebra tiles, on student understanding of algebraic linear equations, and comparing it to the impact of concrete manipulatives and no manipulatives. For my methodology, I have chosen an explanatory sequential mixed methods approach, with my quantitative aspect being quasi-experimental and my qualitative aspect using ethnographic tools. I believe that my research will be significant because there are very few studies that compare virtual and concrete manipulatives directly, and many of these feature limitations that preclude generalizability. My study will take steps to address the flaws of these and other studies, and, using an appropriate definition of virtual manipulatives, will create valid data of their impact on learning. I have two research questions. The first is, to what extent does manipulative treatment, concrete, virtual, or none, impact students' conceptual understanding of the solution of algebraic linear equations? And the second, what aspects of the different manipulative treatments create the differences of impact? In my literature review, I found that several studies mention the general scarcity of academic writing on virtual manipulatives. Within the small number of studies that do exist, direct comparisons of virtual and concrete manipulatives only make a small percentage. To define the term a virtual manipulative, many studies accept the following: an interactive web-based visual representation of a dynamic object that presents opportunities for constructing mathematical knowledge. And this definition comes from Moyer, Bolliard, and Spickel from 2002. While this definition was probably sufficient to describe many computer-based tools for mathematics learning in 2002, it is far too general for the wide range of tools that exist today. I intend to differentiate virtual manipulatives, which I see as electronic forms of their concrete counterparts with added functionality, but which require external guidance, and interactive simulations that have the guidance built in. All of this leads to gap number one, the general scarcity of writing, but especially the fact that most of the existing writing about virtual manipulatives focuses on online tools, like the National Library of Virtual Manipulatives, and very little has been written about offline app-based tools. The recent rise of touchscreen tablets in schools makes the study of such apps very important. A few of the comparison studies that exist do not reach a consensus of the impacts of concrete manipulatives versus virtual manipulatives on student learning. Several outright conclude that the two generally have equal impact. Bauk et al. Concur with this view, but they do acknowledge in their case that students in the virtual manipulative cohort demonstrated faster skill growth. One study indicated that the two had equal impact, but the use of virtual manipulatives minimized the negative impact of extraneous demographic variables on student learning. Some studies in the review did reveal a slightly greater impact of virtual manipulatives. One study indicated a higher impact for virtual manipulatives, but only for students who came to the study with higher levels of prior knowledge. Neither type of manipulative in this case had a greater impact with students with lower levels of prior knowledge. And one study concluded that concrete manipulatives had a greater impact than virtual tools. Taken together, I don't really see a consensus here. One may assume that there is muted enthusiasm, greater enthusiasm for virtual manipulatives, but I don't really see a firm consensus. So this is a gap that I see, and with my study, I hope to begin a process of working toward greater consensus. Despite the lack of consensus, many studies list reasons for educators to be positive about the use of virtual manipulatives in mathematics instruction. They mentioned the age appropriateness and sophistication for secondary school use of virtual manipulatives. They reference greater student independence due to built-in feedback. They reference the variability and unlimited supply of the manipulative in virtual form. They mention built-in constraints and supports to reduce the cognitive load of math tasks. They mention that pictorial and symbolic representation can happen concurrently in virtual form. They mention that virtual manipulatives are better at holding student attention, and they mention that the virtual forms can have the potential to level the socioeconomic playing field. My third gap is in the form of a question. Why is there a lack of consensus among researchers given the strength of virtual manipulatives listed above? And the answer may be here the fact that many of the studies referenced thus far feature flaws and or limitations that cause one to question the validity and generalizability of their findings. And here are some of these. Several studies focused on specific populations, particularly students with learning disabilities and autism spectrum disorder, rather than the general student population. Several studies only looked at samples, very small samples of 3 or 4 students. In 2 studies, students had previous experience with the concrete manipulative and no experience with the virtual tool. In one of the studies, the pretest did not contain enough rigor, and so that students had no room to grow when the same tool was used for the post-test. In some studies, mixed manipulative treatments with all subjects made it difficult to discern which was responsible for the impact measured by the post-test. And in one study, students began with a bias against assistive technology, which leads to a fourth gap. The focus on small specific populations that dominates the literature prevents the findings from being generalized to the larger population. I intend to address this gap. Several articles indicated the need for more research on the impact of virtual manipulatives on student learning of mathematics. And so my proposal fits in to address this call. Returning to my theoretical framework in more detail, conceptual understanding and procedural fluency in mathematics instruction. Both of these are important, but traditional mathematics teaching methods of the past have focused on the latter to the exclusion of the former. And we know that the focus on knowing procedures, which I refer to as the how of math, without an understanding of the concepts that underlie them, the why of math, often leads to student difficulty in mathematics. The concrete, representational, abstract continuum and the place of manipulatives in this. The CRA is a research-supported way of using concrete manipulatives to teach mathematics, in which students are taught concepts first, using concrete objects to represent mathematical concepts, followed by representational drawings, and then symbolic notations. The important function of manipulatives is to enable a link between concrete and abstract thinking. So the manipulatives are absolutely foundational to this approach. Manipulatives have been widely touted as valuable mathematical tools. This is derived in part from the theories of Piaget, Brunner, and Schempp, who all agreed that concept development follows a progression from physical objects to representational forms and abstract thought. Care must be taken when teaching with manipulatives to ensure that students make the connection between the concrete and the abstract. Otherwise, they may believe that the manipulative and the symbolic mathematical worlds are separate and distinct. Virtual manipulatives, what they are and their place in the CRA. My feeling is that virtual manipulatives and interactive simulations are two separate things. The distinction for me is that interactive simulations have guidance built in. The student does not need anything exterior to the simulation, for example, a problem to be solved, to use it, and it may even feature guidance in the form of response validation. A virtual manipulative, on the other hand, is merely a virtual version of the concrete counterpart. The problem to be solved is not built in. It must be supplied from the outside of the tool. There may be built-in constraints that disallow some student actions, but the tool does not offer response validation. This part is up to the student. I want to note that I am not claiming that one is better than the other, simply that they are different entities with different uses. For the virtual manipulative, I see it as being sort of secondary to the whole math learning process. The student has a problem to be solved or some sort of mathematical issue to work on, and as a chosen tool, the virtual manipulative is brought into that context as a support and as a help, rather than an interactive simulation where there's a lot more direction and the simulation may end up being more important or more prominent than the actual problem to be solved. Virtual manipulatives have a unique place on the CRA continuum in that they can offer all three forms at once. And at this point I'm going to leave the presentation and show you an example of what I mean by that. So here is my app. It's actually the desktop or the laptop version, but the app version is exactly the same. And this is what I'll be using in the study. It's the Algebra Tiles app by Brainingcamp. And you'll see that I have a model, my equation up here that I'm going to solve. And so I am going to model 2x and minus 3 on one side. So you can see that I am moving the tiles around and manipulating them very much like a student would in the concrete part of the CRA. You'll also see down here that as I build my equation, that the symbolic representation changes. The moving tiles form a concrete representation, but once in between movements I'm left with a still picture, which is the representational. So the C, the R, and the A are all represented here. Now as students go to solve the equation, they're going to, as we know, add 3 to each side here, but that is very abstract. They can actually do this in the app, adding 3 to one side, and as I add 3 to one side, you can see that the symbolic representation changes down here. When I add 3 to the other side, you can see as soon as I let go of it, the 5 will turn into 8. So we've got the representation here. Now this is the feature right here which really caused my student this year to to realize what was happening at this point of solving equations. As we make our zero pairs, they actually disappear. And this had a deep impact on her understanding. Okay, and at this point I'm going to divide by 2, and I represent that by doing this. And then I need to divide this part by 2, and then I have my solution down at the bottom. Each one of these is actually solution x equals 4. Okay, so that's how I'm showing that virtual manipulatives actually at the same time, at one time, are showing all aspects of the CRA continuum. Returning to my methodology in greater detail, as I said before, I'm going to be using an explanatory sequential mixed methods approach, with the first part being quasi-experimental as I go after my quantitative data. And here is what it will look like. There will be a pre-test, which is the contrasting cases algebra assessment made by the folks at Harvard University. And it will be administered and evaluated directly before the intervention phase. The intervention phase will consist of 4 lessons delivered over the period of 1 month, and these will focus on solving variable linear equations, taught to 3 cohorts under different manipulative treatments: concrete, virtual, and none. For the post test, we will use the same tool twice, once directly after to measure immediate impact, and again once a month later to measure retention. Now, this phase will tell me what the impact is. It will measure the impact and tell me that which of the 3 cohorts experienced the greatest positive impact to math learning. It will not tell me why. It will not tell me the reasons. And that is why I have my second part, which is the qualitative data, and I'll be using ethnographic tools, observations, field notes, and interviews of a sample of all 3 cohorts to discern the reasons behind any difference of impact, as noted by the qualitative data. So I think my methodology fits my research problem and questions perfectly, because I need the 2 parts to create a full picture of what is happening in student understanding of algebraic expressions. The first part will identify where the greatest impact is. The second part will give me reasons for that impact. Site selection and participant recruitment. So after ethics board approval, I will make a short list of schools with the following criteria. I will be looking at schools that are at or below provincial average on EQO assessment for grade 6 mathematics. I want schools large enough that they will have straight grade 7 classes instead of split classes. For simplicity's sake, I would like to work exclusively in straight grade 7 classes. And I would prefer to have a school that is large enough to house 3 grade 7 classes so that the entire study can occur in one location. My reasoning here is that if everybody is in the same school, if all the subjects are in the same school, there's a greater likelihood that they will have experienced a more consistent and uniform math background, and that will hopefully reduce my chance of other variables that I can't control. Then I will approach the school administrators via their district offices, and once I achieve their approval, I will present the study to grade 7 math teachers, accept volunteers, and from there recruit student subjects via information and permission forms. In those forms, I will guarantee anonymity by withholding names and or using pseudonyms for all students, educators, schools, and districts involved. All the data will be stored on an encrypted laptop and then destroyed 5 years after the completion of the study. For data analysis, my dependent variable will be student understanding of solving equations as measured by the contrasting cases assessment. My independent variable will be the definitions of the 3 cohorts by manipulative treatment. And I will be using analysis of variance, ANOVA, to look at the data. Qualitative, I will be using deductive thematic analysis, and as I have an hypothesis, being that the virtual manipulatives will produce the greatest positive impact on student learning, I will be using this to prepare themes in advance based on the literature and prevailing theories. I will also be using inductive thematic analysis, which means mining the data for new, unanticipated themes. I will employ multiple coders and have them compare work for validity to achieve inter-coder agreement. Additionally, I will be going after intra-coder agreement, and to do this I will have individual coders revisit their own work 2 months after the fact as another method of ensuring data analysis validity. And we will be using the constant comparison method. As new data is analyzed, it will be compared to that which has already been studied. In this way, our categories will continue to evolve. I've mentioned a few ethical considerations, but here are a few big points. I will be absolutely clear and transparent to all parties involved about the purpose and methods to be used in this study. I will obtain written consent at all levels. I will guarantee that all reasonable measures will be taken to protect the anonymity of all persons involved. And I will make published results fully available to all who participated in the study. Significance of the proposed research. I believe that I will be able to offer valid and generalizable direction on the use of virtual and concrete manipulatives, in this case algebra tiles, in the instruction of solving linear equations. And on a bigger scale, while this study scope may not be wide enough to solve the debate once and for all, it may be the first of a series of investigations that look into the virtual concrete question with different math topics and different types of manipulatives. Limitations. Because I'll be conducting the research in the classroom rather than in a controlled lab, I will be open and susceptible to more uncontrolled variables. This weakens any claim to causality that may result from this study. As well, the specificity involved in choosing one concrete manipulative and one virtual manipulative to work in the context of a narrow band of mathematics affects the generalizability of the results. On one hand, this study embraces a larger population than many referenced in the literature review. On the other, the results may not be applicable to teachers and students' work in other areas of math. For this reason, this study is viewed by the researcher as the first in a series. It is hoped that the series will provide a more complete picture of the debate over virtual and concrete manipulatives. And my final slides give you some information on the validity and reliability of my quantitative tool. And afterwards I have my list of references used in this presentation. Thank you very much for your attention.